Alright, so welcome again everybody. Today we're going to be looking at the periodic table, right? And we will get back into bonding. So to begin with, we want to take a brief look at the development of the periodic table over time, right? In the early 19th century, scientists began trying to classify elements, right? This is what brought about the present-day periodic table. It's basically a classification of all known elements to men, right? First we had Johann Dobreneur, right? He proposed something called the law of triads, where he observed that certain groups of three elements, which he called triads, seem to exhibit similar type of chemical and physical properties, right? Now what they did is he arranged them in order of increasing relative atomic mass. Remember, we talk about relative atomic mass when you're doing atomic structure. And the atomic mass of our atom is really made up of what we find in the nucleus of the atom, right? The middle element's relative atomic mass was approximately the average of the first and third elements. So, for example, the relative atomic mass of lithium, sodium, and potassium is 7, 23, and 39 respectively. So if we add the 7 and the 39 and we find the average of that, it'll be somewhere around that middle figure of 23. Yeah? Then we had John Newlands. This was in 1865. He proposed the law of octaves, where he arranged known elements according or in order of increasing relative atomic mass and discovered that each element displayed similar chemical properties of elements 8 places ahead of it in a sequence. So, for example, sodium was 8 places ahead of lithium, and both had similar properties. Right? So as you organize these similar elements into vertical columns, which we currently call groups in our modern day periodic table, we realize that those elements shared chemical and physical properties, which still is the same today when we see that when we're looking at trends in our periodic table. Then we had Dmitry Mendeleev, 1869, who published his periodic classification of elements, where he arranged elements by increasing relative atomic mass. So it was based on some of the studies of past scientists, and he grouped elements with similar chemical and physical properties into vertical columns, which we call groups, right? There was some gaps where he believed undiscovered elements should be, and he disregarded the order of relative atomic mass to be better classified elements into chemical families. And this brought about this what we refer to as groups, group 1, group 2, right? Mendeleev is credited with creating the first version of our modern day periodic table, Mendeleev, right? Then we had Henry Moseley. Henry Moseley organized elements by increasing atomic number, right? This resulted in elements with similar properties being placed in the same group. And this led to our modern day periodic table, which is composed of vertical columns called groups and horizontal rows called periods. Now, when we organize or arrange them in this basis, what we see is we have increasing atomic number, right? I sent in a group chat earlier today a snippet of the periodic table. And if you look at that, you'd see that the elements are arranged in increasing atomic number, right? And for that reason, the electronic configuration could be told from our atomic numbers, and the way in which they are arranged, we'll see shortly. We could also determine electronic configuration and some of their properties just by looking at where they're placed in terms of groups or periods. Now, when we arrange the elements in this manner, what we found is that the metals were always on the left-hand side of the periodic table, and non-metals were found to be on the right-hand side of the table, right? Smack in the middle of it, we had what we call transition elements, and we'll get to that shortly. So the groups are the vertical columns of elements. There are 18 groups, 8 of which are numbered, sorry, there are 8 groups, 8 of which are numbered using Roman numerals. Just fix that one time. 8 groups. Right, we have numbered from 1 to 7, and the last group we call group 0. All the elements in the same group have the same number of valence electrons, meaning the electrons on the outermost shell. And for elements in groups 1 to 7, the number of valence electrons, meaning the electrons on the outer shell, is the same as the group number. So for example, elements in group 1, we will notice that there's 1 electron on the outer shell. Elements in group 2 will have 2 electrons on the outer shell. Elements in group 3, 3 electrons, and so on and so forth. So an element in group 7 will have 7 electrons on the outer shell. All of the elements in group 0, right, or group 8 sometimes referred to, have a full outer electron shell, right? Those are the noble gases. They are inert. They do not react because they have a complete outer shell. When we were looking at bonding last week, we saw that all elements are always striving to get a complete outer shell. And this is what makes them reactive. Now, as you move down any group, each element has 1 more electron shell than the element directly above it. All right, so as you come down the group, you are increasing in the number of electron shells, right? This will also determine a larger atomic radii in terms of the size of the atom. The atom is going to continuously increase as you go down the group. Elements in the same group have similar chemical properties, and this is owing to the number of electrons on the outer shell. So elements in group 1 will exhibit similar chemical properties because they all have 1 electron on the outer shell. So they will react in a similar way with other atoms or molecules. As you move down the group, the metallic nature of elements increases and the non-metallic nature decreases. When we say the metallic nature of elements increases, metals, as we saw last week when we was looking at bonding, tend to be willing to donate or give up electrons. So they lose electrons to become cations. Now, what is happening as you move down the group, as I mentioned before, you are getting successive electronic shells. So what that means is that the size of the atom is getting bigger, wider, if you want to call it that. As it becomes wider, it is further away from the nucleus. Remember, in the nucleus, we have a positively charged proton and a neutrally charged neutron. The neutron doesn't have a charge. So what we have happening is this. Right? So if you could see this tiny here. Right? So, 1 second, sir. Right. So look at this, right? We have the nucleus of the atom. Can you see that? Yeah? But it's a little higher. See that? Inside of the nucleus, this is positively charged. Not seen it? Seen it? All right, so yeah, seen it earlier? All right, so I can do better. Okay, we go on the whiteboard on the computer. Let's see. Want one note. Right. So now everybody should be able to see. Well, now we have our blackboard, right? Now whiteboard. So this is our nucleus of the atom, right? The nucleus has a positive charge. Let's change the color of this. I'll write this. Right. The nucleus, inside of the nucleus, it is positively charged. Agreed? Now let's draw a couple shells around it. That's one shell. I'm gonna draw another one here. Positively charged nucleus. Two shells. Another one here. Positively charged nucleus. Three shells. Now let's compare these two, right? Now we have electrons floating around here, right? Electrons on the outside of these nuclei. Now, the center of the atom is positively charged and the electrons on the outside are negatively charged. And we know that opposites attract. Agreed? Everybody agree with this? But as we go down the group, what we have happening is you are having additional shells being added. So this particular element here, right? Let's just take off one of these electrons. Right? Let's just say that each of these was in group 1. Every time we go down the group, the size of the atom is getting bigger. You could see it visually here. Here we have one shell, here we have two shells, here we have three shells. So what is happening is that these valence electrons on the outside here are getting further and further away from the nucleus. Everybody can see that? Everybody agrees with that? Additionally, every successive layer of electrons or shells is creating a whole barrier of negatively charged particles that is shielding the outer shell from the positive attracting forces of the nucleus, right? Because opposites attract and similar charges will repel. So these electrons on the inside is shielding this away from this attracting positive force here in the nucleus. So what happens as you go down the group, the atomic radii or radius increases. And what we will notice is the ability of the nucleus to hold or to attract these strongly decreases. So it easily gives up the outer shell electron. Because the further away this outer shell electron gets from the positively charged nucleus, the less forces of attraction is going to hold that electron in. So what we find happening as you go down those groups of metals is that the larger the atom gets, the more reactive they will be. Give me a thumbs up if you understand that. Everybody understand that? Makes sense, right? So the more we go down that group, the larger is going to be. Right, let's go back to our slides. Right, so as you move down the group, the metallic nature of elements increases. The metallic nature is the ability for it to give up electrons, the ease at which it will ionize. and the non-metallic nature decreases. That's its ability to attract electrons, right? So between groups 2 and 3, there are 10 groups of elements called transition elements, right? Transition metals usually have 2 valence electrons. So we look at those separately, right? Not in today's lesson. Now the horizontal rows going from left to right in a periodic table is what we refer to as periods. And there's a total of 7 periods numbered 1 to 7. Elements in the same period have the same number of electron shells. So when we come down the group, we are increasing in order of electron shells. But if we think of going across the group, we are just, as we move from one element to another across a group, we are just increasing in our electron number. So the same shell is being filled, because remember, we're going from 1 all the way to 8. And then when we go to the next period is where we're going to add on another shell. So the number of occupied electron shells correspond to the period number. So if we are in period 1, it means that we have 1 shell. If we go down to period 2, we're going to have 2 shells, right? As you move from left to right across the period, each element has 1 more electron than the one before it. So as I go from this element on the left to another element on the right, I'm increasing electron number by 1. All right? Additionally, as you move from left to right across the period, the metallic nature of the element decreases while the non-metallic nature increases. So as we move and we go across, remember, we are increasing in the number of electrons on the outer shell. And what we saw is that our non-metals were the ones with larger numbers of electrons on the outer shell. So as the number of electrons increases on that outer shell, their ability or the affinity to give up electrons decreases. Rather, instead, they will now want to attract electrons to complete that outer shell. So take, for example, chlorine. Chlorine has 7 electrons on the outer shell. It is easier for chlorine to gain an electron to complete the outer shell as opposed to lose the electron. So metals, or the metallic nature, is that ability to give off or give up electrons. So elements in groups 1, 2, and 3, they tend to want to give up the extra electron because it's easier. It requires less energy to give up the extra electron, right? Elements in 6 and 5, 6, and 7 want to attract electrons to complete their outer shell, all right? So here's the periodic table, right? Going down in red, you're seeing the periods 1, 2, 3, 4, 5, 6. As we go across a period, right? As you go across a period, we are increasing in number of electrons. 1 more electron is being added. As we go down a group, we are increasing the number of electron shells. The size of the atomic radii is getting bigger. The blue boxes represents our metals, and the yellow boxes represents our non-metals. As we go from left to right, we move from being metallic to being non-metallic, right? As we go down the group, the metallic nature of the element increases, right? That's that ability for it to give up the electron. As we go across the group, though, from left to right, the non-metallic nature increases, right? Also, as we go up the group, the opposite of going up the group, our non-metallic nature increases, right? So fluorine is the most reactive non-metal, whereas francium will be the most reactive metal. Why? Francium has a very large atomic radii, so it will readily give up that lone electron on the outside of its shell, right? Fluorine, on the other hand, is very small in terms of its atomic radii. Look at it. It's in period 2. So there are only 2 shells for fluorine. So its ability to attract an electron is going to be much higher, right? Because it's 2 electrons, it's a small atomic radius, sorry. So it's close to that nucleus, that powerful positive attracting force of the nucleus is going to easily or swiftly pull an electron towards it. Everybody understand that? Yeah, thumbs up if you do. Right, so moving on. Electronic configuration and the periodic table. So based on what we just discussed, we can determine the atomic structure from the group and period numbers, right? the electronic configuration of an atom could be determined if we know its group and period numbers. Conversely, right, alternatively, if we know the electronic configuration of an atom, we could tell which group and period it belongs to, right? So the group number corresponds to the number of electrons on the valence shell. So if an element is in group 2, we know there's 2 electrons on the outer shell. Right? If there are 2 electrons on the outer shell or 3 electrons on the outer shell, then we know that particular atom belongs to group 3. The period number corresponds to the number of electron shells that is occupied, right? So if we have an element that is in period 3, right, that means that we have 3 electron shells, right, filled electron shells. Similarly, if we know the electronic configuration, let's say our atom has the electronic configuration 2881. 2881 will tell me that there are 4 electron shells. All right, 4 electron shells in total. So here are some examples. Potassium is in group 1 and period 4. What information can I get from that? It tells me that potassium has 1 electron on the outer shell. That outer shell, I recording it, Juana Maria. So we introduce the periodic table. We introduced the periodic table today. So far we talked about the history of the periodic table, who were the contributors to the periodic table. Then we went on to talk about how the periodic table is arranged. So we said it's arranged in groups, coming down from top to bottom. There's a total of 8 groups, 1 to 7, having 1 or 7 electrons on the outer shell. And the last group, it's called group 0 because there's a full outer shell. Right now we're talking about how we could identify the atomic or the electronic configuration based on group number and period number. The period is looking at the horizontal rows in the periodic table. And what we saw is that as we go from period to period to period, it tells us the number of electron shells, right? So potassium is in group 1, period 4. That means that potassium has 1 electron on the outer shell. The number of electrons on the outer shell, right, could be determined by the group something element belongs to, right, Juana Maria? So if something is in group 1, it has 1 electron on the outer shell. If it's in group 2, it has 2 electrons on the outer shell. Group 3, 3 electrons on the outer shell, and so on and so forth. The period tells us the number of electronic shells occupied. So potassium, I'm saying here, is in group 1 and period 4. Knowing that it's in period 4, it means that we have 4 shells of electrons. And we learned when we were doing atomic structure, the number or the total number of electrons that could be accommodated on each shell. So based on this information, potassium being in group 1 and period 4, we could tell that the electronic configuration will be 2881, right? 4 shells, and the last shell has to have 1 electron on it. Alternatively, if we have the electronic configuration of an element, so for example, on the right of the screen, we see silicon. Silicon has the electronic configuration 284. From this information, the last shell that has 4 electrons is going to tell me the group that it belongs to, right? So silicon belongs to group 4 because there's 4 electrons on that outer shell. And then I'm seeing that it occupies 3 electron shells. We have an electronic configuration of 284. So that means that silicon is in group 4 and period 3. Everybody understand that? Give me a little thumbs up if you do. Good. Okay. Aliyah, you okay with that? Juana Maria, all right with that? I know you joined in a few minutes ago. So the group number tells us how much electron is on the last shell or the outer shell. And if we look at the electronic configuration and we see something like 284, that tells us the number of shells or the period it belongs to. Okay. So here's an exercise for us to get some practice with it, right? Now, what is the electronic configuration of sodium? So there's a table that I had you guys complete at the beginning of classes, right? I told you that table is going to be like a Bible. So you're going to refer to that table. You're going to write for me the electronic configuration of the sodium atom. And then I want you to tell me what group it belongs to, right? You can also use your periodic table. I just want to include that. 1 second. So I'll just fix this. So you have 10 questions. What is the electronic configuration of sodium? What group does it belong to? Which group and period does magnesium atom belong to if its electronic configuration is 282? What is the electronic configuration of chlorine? And what period is it in? If an element has electronic configuration 285, which group and period does it belong to? Right, so this is what you're going to work on for me, and then we will verbally answer them after you finish. So I'm giving you guys what, a minute or question? Probably like 7 minutes or so, I think should be fine enough. So let's correct these. So what is the electronic configuration of sodium? Alia, you want to tell me the electronic configuration of sodium? It will belong to group 1. Correct, right? So we could look at our periodic table. Right here, sodium. The atomic number of sodium is 11. Right? So the electronic configuration will be 281, and it belongs, you can see here that it belongs to group 1. Very good. Which group and period does magnesium belong to if its electronic configuration is 282? Ravad? Yeah. Period 3, group 2. Very good. Right? Because we could tell from the number of electronic shells that it is in period 3. There's 3 electronic shells, right? And it belongs to group 2. Outer shell electron is going to tell us which group. Juana Maria, what is the electronic configuration of chlorine and what period is it in? So, when we have the electronic configuration, my definition is 287. So the number of shells that we have occupied is going to tell us the period. How much shells is occupied? So the first shell you have 2 electrons on, second shell you have 8 electrons, and the third shell you have 7 electrons. So how much shells in total? There with us? So we're looking at 3 shells in total, right? The first one we have 2 electrons, sorry. Second shell we have 8 electrons, and on the third shell we have 7 electrons. So the number of shells is going to tell us the period it is in. So because we are occupying 3 shells, the period chlorine will be in will be 3. You understand now? Give me a thumbs up if you do. You okay with that, Juana Maria? Yeah? Let me know if you understand, or if you want me to draw it so you get a visual picture of it. I think she said her phone giving some trouble. Okay, good. Yes, she messaged. All right, number 4. If an element has the electronic configuration 285, which group and period does it belong to? Aliyah? I don't, and we're not hearing you clearly. You're not, right. Very good. So it belongs to group 5 because the outer shell electron has 5 electrons, and it's in period 3 because you're occupying 3 electron shells. There's 2 on the first, 8 on the second, 5 on the third. Very good. Rava, determine the electronic configuration of an element in group 2 and period 4. Group 2 and period 4. Right, Rava likes to type, so we look for it across here. Electronic configuration of an element in group 2 and period 4. 2882. Very good. Right, you understand that one, Maria? So since it's in period 4, it means that we're going to have 4 electron shells, right? And because it's in group 2, it means the last shell is going to have 2 electrons on it. So we're going to fill 4 shells. We're going to have 2 on the first, 8 on the second, 8 on the third, and then finally the last shell is going to have 2 electrons because it's in group 2. All right? Number 6, Juana Maria. Which group and period does an element with electronic configuration 286 belong to? Right, so the last shell tells us the group, and the number of shells tells us the period. What you gonna get for this one? Okay, I think our phone giving some trouble. Aliyah, can you help me with this one? Number 6. Mhm. Right. Group 6 and period 3. Very good. 7. What is the electronic configuration of a calcium atom, and state which group and period it belongs to? Ravad, you want to do that one for me? Electronic configuration of calcium and which group and period it belongs to. So here's our periodic table, right? You can see calcium here. Its atomic number is 20, right? So we're going to have 2, 8, 8. What again? 16 and 2, 18. And then 2 electrons on the outer shell. So 2, 8, 8, 2. And it will be in group 2, period 4. Okay? Number 8, identify the group and period of an element with electronic configuration 283. Aliyah, you want to do that one? Very good. If an element has 4 occupied electron shells and 1 valence electron, what is its electronic configuration and its position on the periodic table? Want to help you with that too, Aliyah? It would be right. And where would it be on the periodic table? The right, the left, or the middle? It will be left. Very good. And last one. What is the group and period of an element with the electronic configuration 287? All right, excellent. Right. So just by knowing our electronic configuration or knowing the group and period element belongs to, we could determine the either electronic configuration, we could determine where it will be in the periodic table, and what we will see now is that we could also determine how it will behave chemically in terms of its reaction. Now we are going to look at some trends in some of the groups and some of the periods on the periodic table, not all of them at this level. All right. So the first one we want to talk about is our group 2, which is also referred to as the alkaline earth metals. Now, elements in group 2 have similar chemical properties because they each have 2 electrons on the outer shell. Now, the chemical properties or the way in which an atom would behave chemically in terms of its reaction is always based on the number of electrons on the outer shell. So it goes without saying, if we say that the number of electrons on the outer shell determines the chemical reactivity of an atom, that atoms that belong to the same group will show similar chemical properties, right? Similar. So they tend to react, the group 2 elements, they tend to react by what? Losing or gaining electrons. Is it easier for them to lose electrons or gain electrons? What do you all think? Anybody can answer. Is it easier to lose or gain electrons? To lose electrons. Why? Because they just have 2 electrons on the outer shell. Yeah? So what we say is that the ease of ionization is greater for the group 2 elements, right? When we use the word ionization, that's a big word that we're using to describe the process by which atoms could lose or gain electrons to form ions. So we say that these group 2 elements, right, react by losing the outer shell electrons to form positively charged ions. And last class we learned that positively charged ions are called cations, right? So this is the process of ionization. So the more easily an element ionizes, the more reactive it is. So it easily loses its outer shell electron, right? And what we will see, as I mentioned before when I drew the diagrams, is as we move down the group, that ease of ionization increases. Why it increases? Because the size of the atom is getting bigger. So the outer shell electrons are further away from that positively charged nucleus. It's further away from that pulling force of those positively charged particles inside of there. So you find that the ease at which it will lose those electrons increases as we go down the group, right? In the table I have here, we have the atomic radius, right, increases moving down, right? And this is due to the increase in the number of occupied electron shells. When we drew the diagram before, we are seeing that as you go down the group, you have successive shells creating additional layers like an onion. As we go down, the atomic radii is increasing. So the attractive pull of the positive nucleus on the valence electrons is decreasing. So the more easily the atom lose their valence shell electrons to form cations. So the most reactive element in group 2 will be where? To the top, the middle, or the bottom of the group? What do you think? Most reactive. Top, middle, or bottom of the group? Most reactive element. Would it be beryllium? Or is it, I believe that's radium there. Radium. Where will it be? At the bottom, radium. Right, so this is our group 2. We have beryllium, magnesium, calcium, strontium, barium, and radium. The most reactive here is going to be radium. You see the atomic number? 88. Right, now there's as you go up in successive shells, some of the outer shells, larger shells, they actually accommodate more electrons, sometimes up to 16. Right, we only need to do up to 20 elements for CXC. And what I'm saying is that as you go down the group to radium here, you have larger volumes of electron shells. And those electron shells are further away from that positively attracting nucleus. And the further they are away from it, it's the less force of attraction the nucleus has on those outer shell electrons. So we have an increase, right, in our ease of ionization. Right, so your reactivity with things like oxygen, water, dilute hydrochloric acid is going to increase as you move down the group. The reactions are going to become more vigorous, sometimes violent, as we go down the group. Why? Because the reactivity is increasing as you go down the group. Everybody understand that? Yes? One of my back in. Right, so we was just talking about the just to recap quickly for Juana Maria, right? We wrapped up these questions, and what we saw is that the electronic configuration could help us determine which period an atom or element will belong to, and the outer shell will tell us which group it is in, right? So these here are our groups coming down the periodic table, right? So everything here in this column is in group 1. If we check the electronic configuration, this will be 2-1, this will be 2-8-1, this will be 2-8-8-1. The period is telling me the number of electron shells. So lithium is in period 2. So that would only have 2 shells. If we look at the electronic configuration, we'll just get 2-1. Sodium is in period 3. So we'll get 2-8-1. The 1 corresponds to the group number. If I randomly take one here, let's say bromine. Bromine is in period 4 and it's in group 7. So I should get 2-8-8-7. You see how to use it, Juana Maria? Now, other than that, right, the periodic table could also tell us about the behavior of similarly type elements or elements found in the same group. We refer to those as trends. And we are looking at group 2, right, just before you jump back in. And we said that group 2, also called the alkaline earth metals, right, as we go down that group, the number of electron shells increases. We have 2 for beryllium, 3 for magnesium, 4 for calcium, 5 for strontium, 6 for barium, and 7 for radium. As that happens, the size of the atom is gradually getting wider. It's increasing. The atomic radius is increasing. Why? Because we have more shells being added as we go down the group. So radium is going to have 7 shells. If you think of it like an onion, it's going to be a bigger onion than beryllium, which might just have two layers, right? Now, what happens is that in the middle of the atom, you have a nucleus that is positively charged and attracts the electrons there. But the bigger the atom gets, the further away the outer shell electrons are from that positively charged nucleus. So the less force of attraction is exhibited or exerted on the outer shell electrons. What that means is, like for elements like radium that has 7 electron shells, the outer shell is further away from the nucleus, and it can be easily lost. It can be easily given up because the pulling force of attraction from the nucleus is less because it's so far away. That ability for the atom to lose and in some cases gain electrons is called ionization. So as we move down group 2 and the size of the atomic radius increases, the ease of ionization, the ability for it to lose the valence shell electrons to form cations, which are positively charged ions, that increases, right? Because that the pull, the attractive pull of the positive nucleus decreases. You okay with that one, Maria? Now, for that reason, the reaction of group 2 elements with things like oxygen, water, and hydrochloric acid increases as we go down the group and becomes actually more vigorous or violent. So the way in which beryllium would react with water wouldn't be the same as radium. Radium might be violent, right? Very violent and vigorous reaction. So these are some examples of reactions with calcium. Now, it doesn't matter which group 2 element that we use, the reactions will pretty much be that they will produce the same things, right? With oxygen, you will produce some metal oxide. So here we get calcium oxide. If I use barium, I will get barium oxide. Radium, I'll get radium oxide. And the formula will be the same. Right? So you could just swap out this calcium for any one of the other group 2 elements and it will be the same reaction. With water, calcium reacts with water to form what we call here, this is called calcium hydroxide, and it produces hydrogen gas. So again, I could swap out this calcium with any other element in group 2, right? If I want to use beryllium or magnesium, I will just remove the calcium from here and put the symbol for beryllium or magnesium. The formula will remain the same. Same thing happens with hydrochloric acid. Calcium and hydrochloric acid gives us calcium chloride, which is a salt, and hydrogen gas, right? Similarly, if I use radium, I'll get radium chloride and hydrogen gas. Everybody understand how the reactions work? Give me a thumbs up if you do. Yeah, Aliyah, good. Ravad, are you all right? Juana Maria, we good? All right. So we looked at group 2, which is the alkaline group metals. Now we're going to look at group 7, which is the halogens. Now the halogens exist as what we call diatomic molecules. So they're not going to be found by themselves. They will always pair with each other. So 2 fluorine atoms will join together and form a molecule. We call it a diatomic molecule, right? Oxygen exists as that as well. So all of the elements in group 7 exist as diatomic molecules, right? Now they have similar chemical properties because they have the same 7 electrons on the outer shell, right? They have 7 valence electrons. Now these elements in group 7 all react by what? Gaining or losing electrons. Anybody can tell me? Do group 7 elements gain or lose electrons when they react? I think Juana Maria. Is it Juana Maria? Or Aliyah? Gain or lose electrons? Ravad, you want to try this one for me? Do group 7 elements gain or lose electrons when they react? Yes. Go ahead, Aliyah. Yeah, he just answered. They gain, right? They gain electrons. Why? Why do they gain electrons, Aliyah? Why do they gain electrons? Yeah, because they have a large number of electrons on the outer shell, right? 7. So it's easier for them to gain than to lose. Now, when they gain these electrons, do they become positively or negatively charged? Revan, positively or negatively charged? All here, negatively charged. And why is that? Right? And that process of reduction means what? In terms of number of protons and number of electrons. They will gain. So if they gain, they get in more. So you're doing what? You're increasing the electrons. Yes. Right. And if we increase the electrons and the number of protons remain the same, then we have more negatively charged particles than positively charged particles. And that is what has resulted in that negative charge, because we have more electrons than protons. So, for example, with chlorine, chlorine is what? 17, right? Has 2, 8, 7. That's its electronic configuration, right? When it gains an electron, it has 288. The number of protons is still 17, but now I have 18 electrons. And from our maths, plus 7 minus 18 will give us what? Plus 17, sorry. Plus 17 minus 18 will give us. You have to work that out, like sign integers. Plus 17 minus 18. Anybody? What do you get? Minus 1. And that's how we get in that negative charge. Because our number of electrons is greater than our number of protons. Now, this process of gaining electrons is also called ionization. Ionization involves either losing or gaining electrons, right? However, the ease of ionization, which is its ability to gain electrons, increases as we move up the group. So whereas with the alkaline earth metals, the ease of ionization had increased when we go down the group. Why? Because it got a bigger radius, right? And as you got a bigger radius, the electrons on the outer shell further away from the positively charged nucleus. So it's easy for them to just drop off that electron. With the halogens, the opposite is happening. Remember, they want to gain electrons. So you want to be closer to the positively charged nucleus to attract electrons. So the smallest one, which is fluorine, which has a small atomic radius, is going to have the greatest attracting power. Why? Because you have a smaller number of electron shells, so it is closer to the nucleus. So the ease of ionization increases as you go up the group, right? Or we could say the ease of ionization decreases as you go down the group, right? So the elements or the element that will be most reactive will be where? To the top, middle, or bottom of the group. Where do you think the most reactive element will be in group 7? Top, middle, or bottom? It's an open floor. Anybody can answer. Top, middle, or bottom? Would it be to the top of the group, the bottom of the group, middle of the group? Where would be the most reactive element in the halogens? It would be to the top of the group. It would be to the top of the group, right? Because that has the smallest atomic radii. Right, let's take a look at that. So here we have fluorine. The appearance and state at room temperature. It's a pale yellow gas. The number of electron shells occupied, just 2. So the atomic radius is very small. So the atomic radius increases moving down due to an increase in the number of occupied electron shells, right? The ease of ionization, though, increases as you move up the group because the atomic radii is the smallest to the top, and the attractive pull of the nucleus on electrons to be gained increases as you go up the group, right? It means that the more easily the atom gains the electron to form an ion, it means it requires a smaller atomic radii, and the smallest atomic radii will be fluorine. So reactivity is going to increase up or down the group. How is reactivity going to increase? Going up the group towards fluorine or going down the group to iodine? What's your take? Anybody can answer that for me? No? Alia? Going down or going up? Going up, right? Because you have the smallest atom to the top of the group, which is fluorine. And as you go up, the atomic radii is small, so it's closer to the nucleus, and group 7 elements need to attract or gain electrons. So you want a small radius closer to that attracting power to pull in the electrons, right? Strength of the oxidizing power. So the strength of the oxidizing power is the ability of the electrons to take electrons from another element. So last day we said oxidation is the loss of electrons and reduction is the gain of electrons, right? The elements that are reduced, meaning gain electrons, are called oxidizing agents. So a bit of reverse of the names. So an element that could be easily reduced, meaning that gain electrons, is called an oxidizing agent. Means it facilitates oxidation then, which is the loss. You understand? Everybody understand what I say there? An element that is reduced or reduces, meaning that it gains electron, is an agent for oxidation. It facilitates another element losing the electrons because they are going to gain it. So that ability to oxidize something increases as we go up because the element fluorine to the top has the strongest pull because it has a small atomic radii and the nucleus is going to easily pull an electron, let's say from sodium, right? Displacement, right? Displacement means the ability of one atom to displace other, to kick it out and take control, right? You know, like in physics, when you talk about displacement, you drop a you have a displacement tank, and if you want to measure the volume of something, you drop it inside of there, right? And the water that comes out, the water that is displaced, is how you measure the volume, right? So think about it the same way. When we talk about a displacement reaction, we are talking about a reaction where one of the elements, right, is going to, an element in its elemental form replaces another element within a compound, right? The more reactive element will displace the less reactive one. So in group 7, the most reactive element is the one to the top of the group. So elements to the top of the group could displace those at the bottom of the group, right? So for example, chlorine will displace bromine and iodine from their compounds. Why? Because chlorine is above bromine and iodine. Let's go back to our table, right? Look at group 7 here. Chlorine is to the top, then chlorine, then bromine, then iodine, then astatine, right? Anything to the top is going to displace something from the bottom. So if we have let's say we have something like potassium chloride, and we put fluorine in the mix there, chlorine is going to kick out that chloride and make potassium fluoride instead. Understand? If we have something like potassium iodide and we put chloride in the presence of that, chlorine is going to kick out the iodide and make potassium chloride instead. Everybody understand what I'm saying there? Give me a thumbs up if you are. Everybody understand what I'm saying? So here are the examples. Chlorine will displace bromine and make potassium chloride for the bromine. Displacement reactions are understood by considering the relative strength of an element's oxidizing power. That's the ability to gain electrons, right? Which measures how easily one substance accepts electrons from another. The oxidizing power of group 7 elements increases as you go up the group, right? Because the most reactive one is to the top. So chlorine can take the electrons from bromine and iodine, while bromine will take electrons from iodide, right? Because it's above iodide. All right, everybody all right to that so far? Yeah? All right, I'm just gonna take a short 2-minute break and then we're gonna continue with trends across period 3. Actually, let's do the trends and then we would look at questions and we can wrap up a little bit. So trends across period 3. So far we talk about group 2, we talk about group 7. So we talk about 2 groups on either side of the periodic table. Now we want to talk about a period, going dead middle, looking at period 3. Now remember, period, we're looking from one side to another, left to right. So the period 3, as we move from left to right, the elements are going to become less metallic and more non-metallic. Because our metals are on which side of the periodic table, left or right? Where are our metals? Are they on the left or are they on the right? Left. Very good, Aliyah. Right? Our metals are on the left and our non-metals are on the right. So as we move from the left where we have more metallic elements, you just said alkaline earth metals was in group 2. And we go across to the halogens, which is group 7. We will see that we are moving from metals to non-metals. Silicon, which is located in group 4, is classified as a metalloid, or another word for metalloid is a semi-metal. It has 3 occupied electron shells, and for this reason, it exhibits both metallic and non-metallic properties. Now, the ease of ionization as we go from metals like sodium to magnesium, aluminum, and we go across the period. Now, we're not going down a group, we are going across, right? It decreases as you go across the period, right? Why is that? The ionization ease and reactivity of non-metals such as phosphorus, sulfur, and chlorine increase across the period. Yeah? The reason for the ionization and ease of reactivity in the metals to decrease is because you are, as you go from the sodium to the magnesium to the aluminum, remember the number of shells is remaining the same, but the number of protons inside of that nucleus is increasing, right? Because in the same period, the electron shells are not increasing. Electron shells are remaining the same, but the number of protons inside of the nucleus is increasing. So that ease at which it will give up that outer shell electron is actually decreasing as you go across the period for sodium, magnesium, and aluminum. We have to look at it as metals and non-metals because the opposite is happening now, right? With the non-metals, the ionization ease and the reactivity of the non-metals will increase as you go across the period from left to right. Why? Because you are increasing the number of protons and the size of the atom is remaining the same. So its ability to attract an electron is going to increase. Everybody understand that? Now in the middle, like silicon, they do not ionize. Instead, it will form what we call covalent bonds. This is a type of bonding that involves the sharing of electrons, right, with other nonmetals. Argon, which is in group 0, is an inert gas. So it does not ionize. It's not going to lose or gain electrons. It is chemically unreactive because it already has a complete outer shell. Everybody understand that? Yeah, thumbs up if you do. Right, so this is what I'm talking about here. Sodium has 3 electron shells, right? But as you go across, these number of protons is increasing, right? So this is why they will be as you go across, it will be less easy for them to ionize. Now they are good conductors of electricity. Silicon, which is in the smack middle, is a semiconductor. And then these to the far right are non-conductors. They're good insulators. In terms of the amount of electrons that they lose, right? You lose 1, 2, 3, 4, 3, 2, 1. Now look at the atomic radius. Can anybody tell me why the atomic radius is decreasing as I go from left to right, even though that I have the same number of shells? Why is it decreasing? We're in the same period 3, but I am seeing the atomic radii as I move from left to right, it is decreasing. Anybody knows why? It is decreasing because we're increasing in number of protons. And the more protons, the stronger it's going to pull those electrons in, right? So the atomic radii decreases moving from left to right due to the increase in the number of positive protons, causing the attractive pull of the positive nucleus on the valence electrons to get stronger. So as you go from left to right across a period, you will find that the atomic radii decreases, right? The ease of ionization. The ease of ionization, as we saw, when you look at your metals, it's going to increase if you move from right to left. The opposite happens just now. We describe it as decreasing as we go from left to right, right? And that's because the atomic radii is getting bigger, right? In the middle, like silicon, does not usually ionize. To the left, the increasing, the ionization increases as you go from left to right. Okay, reactivity is going to increase within the period. Now, look at how they break up the period. You have the middle, which is silicon, that behaves kind of differently. And then you talk about the metals on one side and the non-metals. Because different things is happening inside of the period. Because why? You have metals, semi-metals, and non-metals across a period. Right? So there's 3 different types of behaviors when we talk about reactivity, ease of ionization, right? In a period. Everybody understand that? Give me a thumbs up if you do. All right. So now we go into the final segment of the class, which is questions. So we have 8 questions in total, which is based on today's lesson.